Good morning, our students, and welcome to this hour's discussion. Today, we want to look at something different from what we have been looking at recently. Do recall that lately we have been talking about distribution of what we call sampling distribution. But this morning, we want to look at a topic: convolution of two distributions. First of all, when we talk about convolution in statistics, our interest should go, or our mind should go to that method or rule or principle through which we obtain the distribution of two independent random variables. So assuming we have information that two random variables are independent, and these two random variables have their respective distributions, and then we decide to sum these two random variables, say x and y. And then the interest now is to obtain the distribution of the sum of these two independent random variables. What we have to do is to follow the approach of what is called a convolution. So convolution is a method, a guideline, a principle through which we arrive at the distribution of the sum of two independent random variables. And then for us to do this, we should be considering if these two independent random variables are discrete random variables or continuous random variable. This morning, we want to quickly look at the convolution of two independent distributions where the random variables now involved are discrete random variables. Let us, for instance, call these two independent random variables x and y. So I have two independent random variables. The first independent random variable is x, then the second independent random variable y. And then, of course, this independent random variable x has its own distribution, and its PMF is given by, that is, its probability mass function is given by P of capital S is equal to small x. That is, assigning the probability to every value of this random variable, capital X, which is given as a small x. Then we equally have information that this random variable y has its own distribution, and then equally its own PMF is given as capital P is given as capital Y is equal to small y. So our interest here is to sum these two independent random variables x and y, and let us call the sum z. So I have what? Z is given as what? X plus what? Y. So the concern here is, having known this x and its PMF, having known this y and its what? PMF, how do we arrive at the distribution of this what? Y? Sorry, distribution of this z, which of course is the sum of these two independent random variable x and y. Before we progress, we want you to look at one thing here. From this z equals x plus y, we can decide to make x subject of formula. We can decide to make y subject of formula. If I'm making y subject of formula, for instance here, it implies that my y is given as what? Z minus what? Minus x. My y is equals to z minus what? X. By implication, anywhere I see y, I can replace with the z minus x. And if you agree with me, if I return back here, what I'm going to have becomes that y as a random variable, its PMF is going to be P, I open a bracket. What I have here is y. I now have information that y is equals to z minus x. So I have z minus what? Minus x equals. Here is my y, and I equally have information that my y is already z minus x. But this time around, we are talking about the realization of that random variable. So we write it in small letter. So here it becomes what? Small z minus small what? X. Close the bracket. This and this are the same thing. And it is from this and this that we are going to find the convolution of the two random variables x and y. So for us to find the PMF of this random variable z, which is the sum of these two independent random variables, we are going to say that P of capital Z being equal to small z is given as, we have sum over the range of x of P of capital X equals to small x multiplied by P of what? This our capital Z minus what? X being equals to small z minus what? Minus x. Close it. And let me remind us that of course you know that this our capital Z minus x is equals to y. So I can equally write this that this is equals to sum over the range of x of P of capital X is equals to small x multiplied by P. This my z minus capital X is y, which is here. So I can write what? Y is equals to small z minus small x. So this is the formula that we are going to use each time we are to find the distribution of the sum of two independent random variables x and y. Let us now take one or two questions now, and using this thing which you have shown here this way, solve that problem. So permit me to clean here while we now work one or two questions. The first question I have here says, the first question says here, the first question says, let x takes values, let x take values, the values of x, let x take values 0, 1 with probability that x is equals to 0. So with P of x equals to 0 given as 0.4 and P that x is equals to 1 given as 0.6. So let what? Y take a value as the value of y as 0, 1, 2 with probability P that y equals to 0 given as 0.2, P that y is equals to 1 given as 0.5, and P of y given as 2 is given as 0.3. The question they ask us is compute, that we should compute P of capital Z being small z, where our z is equals x plus y. That is the information that they gave us, that we should compute this. We are going to use that formula that we used before, or that we gave before. And that formula says, I'll come here and divide the line. That formula says that our P of capital Z being small z equals sum over the range of x of P of capital X is equals to small x multiplied by P of capital what Y being Z minus X. And one important thing we need to do is that anytime we consider X and consider Y, the sum must give us Z. So by implication, X plus what Y is equals to what Z at every point in time. And if you watch the value of X here, the value of X here is 0 and the value of Y here is what? 0, the first value. So actually, Z can take a value to be what? 0. So I can have a situation where our Z is equals to 0. Z can be equals to 0 if and only if X is equals to 0 and Y is equals to 0. So it is 0 plus 0 here that can give me this. So if I have X being 0 plus Y being 0, that is only time I can have that Z is equals to 0. And at that point in time, I am going to use this formula now to find the probability that Z becomes what? 0. So I will come here. So my P that my capital Z is equals to 0 equals to. I will now come here and I will say, I will look for a place where my X is equals to 0 and look for a place where my Y is equals to what? 0. The only place there they told me that P of X equals to 0 is 0.4 and P of Y is equals to 0 is 0.2. So this thing becomes what? In place of this one, 0.4 multiplied by, in place of this one I have 0.2. 0.2. So whatever value you get it now is a place where Z is equals to 0. Of course, you can see that I can equally say 0 plus what? 1. If I say 0 plus 1, I am looking for a place where Z is equals to 1, where Z is equals to 1. And let us consider all places where Z can be equals to 1. If I say 0 plus 1 here, that is X plus being 0 plus Y being 1. The answer is going to give me 1, which means 0 of X plus 1 of Y will give me what? 1. Okay? Then I can equally say here that let X now be what? Be 1. Y now becomes what? 0. They will still give me what? 1. So I can equally say X now is 1 plus Y now is 0. The answer will still give me 1. So these are places where the sum of X and Y can give us what? 1. So we are now going to consider this place, plus. That is the essence of this sum. Consider this place and consider this place. So my P of Z being equals to 1 is equals. Here my X is 0. Probably that X is 0 is 0.4. So I have 0.4 multiplied by. Here we have come where Y is equals to 1. Y is equals to 1 here is 0.5. So I have 0.5 plus. We now come again where X is equals to 1. X is equals to 1 at 0.6. So we have 0.6 multiplied by. We come when Y is equals to 0. Y is equals to 0 at 0.2. So this becomes 0.2. So if you evaluate this, whatever value it gives you is the value of a Z being equal to 1. So we are equally going to look at the value of Z equals to what? 2. We have gotten the Z equals to 0 here. We have gotten Z equals to 1. We want to look at Z equals to what? 2. So when Z is equals to 2, let us come here and look at the combination. The only combination that can give us this is when we consider 0 as X and consider 2 as Y. So first of all, we can have what? 0 plus what? 2. The answer will give us what? 2. Or we can consider x being 1 and y being 1. So we can say 1 plus 1, it is going to give us what? 2 still. Or we can equally come and consider that let our y be what? Be 2, while x becomes what? 0. So in that case, our y is 2 and our x is what? 0. So we can have, which of course is what we have considered here. So here our x is what? 0, y is what? 2. But we are considering let y be 2 and then our x can equally be 0. Here our x is 0, y is what? 2. Look at it here. Here, this can be 1 and this can be 1. There is no other combination you can see here that can give us 2 except these two combinations. So we now go and solve it now. So our P of Z being 2 now is equals. We look at where x is 0. X is 0 here when we have 0.4. So this is 0.4 multiplied by. Then where y is equals to 2, y is equals to 2 as 0.3. We have 0.3 plus. We now look for where our x is equals to 1. X is equals to 1 as 0.6. So we have 0.6 times. We look here y is equals to 1 and y is equals to 1 at 0.5. So we have 0.5. So once you evaluate this, whatever value it gives you is the value where our z is equals to 2. Looking at this, there is no other place where you can say let z be 3. If you say z be 3 now, it is only 2 conditions that is going to satisfy it, and we can equally do it. When we say let our z be 3, let z equals to what? 3. What we are going to have here is, we can either say let x be 1 and then y be what? Y be 2. This is the only place where this thing can be satisfied. X being 1 and y being what? 2. That is the only place. And in that case now, we are interested in x being 1 and then plus y being what? 2. This will be able to give us what? 3. And in that case, what we are now going to have becomes what? That our P, that z is equals to 3, will be given as, where this one is equals to 1 is given as this. Where this one is equals to 1 is given as where it is equals to 1 is given as 0.6. So we have this thing become 0.6 multiplied by where y is equals to 2 is given as a 0.3. And whatever value you get here now becomes the probability that z is equals to 3. You cannot get probability that z is equals to 4 because there is nothing to sum from x and y that will be able to give us 4. And then we now say that the probability distribution of z now becomes, so permit me to clean this up and give it very clearly. So we now say that the probability of distribution of z is given as, we have this so we have something like this. This is our z, this is our p of z being small z. So here we began with 0, 1, 2, 3. When it was 0, what we got was this, 0.4 times 0.2. So here is 0.4 times 0.2. Whatever value you get, it is here. When it is 1, it is the entire of this quantity. So you put it here, you evaluate 0.4 times 0.5 plus 0.6 times 0.2. Whatever value you get, you put it here. Then you equally evaluate when z is equals to 2, which is what we have here, 0.4 times 0.3 plus 0.6 times 0.5. Whatever value you get, you put it here. And lastly, whatever value you get, you put it this way. And this is how to obtain the distribution of a new random variable z, where that z is the sum of two independent random variables x and y. We still have more questions to solve under this convolution, but we are going to stop here in order not to make the video too long. Please remain connected to us as we now step into another new and fresh topic that at times poses challenges to students resolving them either in exam or making sense out of it while studying them. We are going to discuss them, solve a lot of problems both under discrete and continuous random variables. Thank you very much and see you in our next class.